Okay, so here are some walkthrough examples from Chapter 1 of the OCR B Advancing Physics course. Question 1. So firstly, we're asked to calculate the power of the camera lens, but we're also asked to explain our reasoning clearly. Now that suggests that we're going to be required to make an assumption and that we need to justify why we've done that. And that lies in our use of the lens equation, which we know is 1 over v is equal to 1 over u plus 1 over f. Now, being asked to calculate the power of the camera lens, what we're being asked to find is 1 over f. Now, if we look at the data that the question has given us, we're being told that the image is focused 0.012 meters behind the lens. So that is our value for v. And we are being told that the distance from the Earth to the Sun, where bear in mind that the Earth is where the camera is based, is 1.5 times 10 to the 11 meters. So that is our value for u. Now, if we compare those two values, when we look at 1 over v and 1 over u, given that u is 1.5 times 10 to the 11 meters, the value for 1 over u is it's practically negligible. It's very, very small. Okay? So that is our assumption that we're going to make here, or our deduction, if you like. Value for 1 over u is practically negligible. And therefore, when we take that into consideration, what we're left with is that 1 over v is approximately equal to 1 over f. And therefore, in being asked to calculate the power of our lens, actually what we're being asked to find is very roughly what is 1 over v. And when we do 1 over v, so 1 divided by 0.012 meters, we end up with a value of 83.8 diopters. So the power of the lens is approximately equal to 1 over v, because we are assuming that in this circumstance our value for 1 over u is almost negligible. Okay, now we move on to working out the resolution of an image. Now, this requires measurements to be taken directly from your image, so it will depend on the size of the page that you've been working for, but the workings behind it, if your numbers follow the same method, then you will have done it correctly, and ultimately you will actually end up with the same answer anyway. So I was taking measurements from a slightly scaled down version. It was an A5 copy rather than an A4, so the exact values won't quite match if you were working off an A4. So we're trying to find the resolution of the image of the sun's corona. Okay, so the first thing we need to do is say, well, okay, we know that the image is 710 pixels tall, but how tall is our actual value of the sun in pixels? Okay, now the way that we do that is we say, well, all right, then how big is that sun as a proportion of the rest of the image? So we measure that. And from my A5 version, the diameter of the sun was 3.1 centimeters, and the height of the entire image was 5.7 centimeters. Okay, so when you do 3.1 divided by 5.7, that tells you what proportion of that 710 pixels the sun actually makes up. So to then work out how many pixels the sun is, we multiply that value by 710, which in my instance gave me 386 pixels. Now again, depending on what your measurements were, you'll find that your value for the total number of pixels for the sun should still come up more or less the same, and anything in the range of 350 through to 430 would be acceptable here. So that tells you the total number of pixels in that image for the diameter of the sun. Now we know that resolution is measured in this case in kilometers per pixel. Okay, and therefore in order to work out the resolution, what we do is we say, well, what is the total distance that image is covering in real life? Okay, and that's the diameter of the sun. So we've got our diameter of our sun of 1.4 times 10 to 6 kilometers, and that is represented by our 386 pixels. And when we do that, I end up with a value of 3626 kilometers per pixel, or 3,600, depending on what you want to do with your sig figs. All right, but again, anything in between sort of 3,200 and 4,000 would be an acceptable value here for the resolution, allowing for variation in measurements taken from the image. So now we're being asked to use the value of resolution that we've just found to work out a real height. So the height that is actually, that point A is from the top of the sun, or from the sun's surface. Okay, so if we go back, this still involves this idea of ratios. So what we're asked to do is say, well, okay, the first thing we need to know is how many pixels are represented by that height there. Because if we know how many pixels there are in that height there approximately, and we know how many kilometers each pixel represents, because we've just worked that out, we are able to work out the real distance that is represented by this arrow that I've just drawn. Now this isn't perfect because obviously you can see my angle isn't completely vertical, but leeway is built into questions for that sort of approach. So what I've done is I've measured the real distance between the surface of the sun and A as a ratio, or rather as a fraction again, of the whole vertical height of the image. Alright, so when I did that, I ended up with a value of 0.5 centimeters for the height itself, out of the whole height of the image, which was 5.7. So that gives me the proportion again of that vertical height, not worrying too much that the line isn't completely vertical. And then we multiply that by our 710 pixels, and that gives us the total number of pixels that that arrow represents, which is approximately 63 in my case. Anything between 54 and 66 would be an acceptable answer here. So that particular distance in the image is 63 pixels, and we know from part A that 1 pixel represents 3,626 kilometers. Okay, so then I take my value for the number of pixels in the in that distance, and I multiply it by my value for the resolution. Okay, and therefore your value for the pixels multiplied by your answer to part A is perfectly acceptable. And when I do that, I end up with a value of 5829, okay, or very roughly 226,000 kilometers. Okay, now again, your answer will vary slightly depending on the readings that you took and the measurements that you took rather, but anything between 170,000 and 280,000 is fully creditable as long as you can show this working. So here we're being asked to describe how a student could observe this relationship between the amount of light being polarized and the angle of reflection. Okay, so this is one where there's a few things you could mention. There's a little bit of leeway in terms of your use of terminology, but what we're really looking for here is, as they currently look through the polarizing filter, okay, they will be able to see a certain amount of light passing through. What they're needing to do here is, in order to see how much light is actually being polarized, they will need to rotate that filter. Okay, so they need to rotate that polarizing filter. All right, as they rotate it, they need to be observing that reflection. All right, so all that time keeping an eye on the reflection that they are actually getting. All right, because as they rotate that filter, they will be able to see what is happening. What they then need to do is, this relationship is all about finding out if the amount of light that's polarized depends on the angle of reflection. So obviously they need to do that, and then they need to change that angle R. Okay, so change that angle R, still observing the reflection. So what they're looking for is, as that angle of R changes, as they rotate the filter, as the filter rotates, they will be able to see maxima and minima of light. So maxima when the filter is letting a large amount of light through, minima when it's letting through much less or even no light at all. And normally you will see that you would move from a maximum to a minimum during a rotation of 90 degrees. Okay, so this idea that a 90-degree rotation would actually show this movement from a maximum to a minimum. Now obviously this will be worded much better by you, but I'm just trying to get the key points in here. Okay, so maximum or minimum, and you could talk about a minimum in terms of zero light passing through, that's absolutely fine. But what we'd expect to be observed is that as you rotate that polarizing filter by 90 degrees, the amount of light passing through, and therefore the amount of light observed, would be changing. Okay, so what you're doing in this instance is you are looking through the filter, you are then rotating it to allow you to observe this change from a maximum to a minimum, or indeed a minimum to a maximum, because that's showing you that the light is in fact polarized, because only when you have the filter in a particular plane are you able to see the light passing through. Then when you change the angle of R, you repeat that process, so you then once again rotate that filter through 90 degrees, and what you should see basically is you're looking to see if the intensity changes. So any 3 there really would get you the marks. Here we're looking at digital image storage and digital image coding. Okay, so we've got an array of 12 by 12 pixels, and each pixel is either on or off. Okay, so each pixel is either a 0 or a 1, and that means that we use 1 digit to code each pixel. Now remember, a single digit is 1 bit. So part A is asking us how many bits we need to store the logo. Okay, so the first thing to do is say, well, all right, if each bit, or rather each pixel is represented by 1 bit, how many pixels have we got in total? Well, we've got a 12 by 12 pixel array, and therefore the total number of pixels is 144. Each pixel is coded with a single digit or a 1 bit code, and therefore the total number of bits for that logo will be 144. We're then asked to convert that to bytes. Remember, to get bytes from bits, you simply divide by 8. So when we do that, we end up with 18 bytes. Then we're asked to look at the total possible number of alternative logos they could consider, assuming that a change to any pixel would form a different logo. So we are saying here that we have got 144 bits. What we're being asked is, with 144 bits, how many different logos are we able to get? Well, to do that, we say, well, okay, 2 to the power of 144 gives us 2.23 times 10 to the 43. Okay, or 2.2 times 10 to the 43 different alternative logos. Here's a nice short answer one here, looking at the effect of a lens on wavefronts. So describe the effect of the lens on the wavefronts. There are 2 ways you can think about this. What do all lenses do? Well, they add curvature. Okay, so the lens adds curvature to the wavefronts. You could also say that it actually focuses the wavefronts. That would be all right too. Okay. Not sufficient to say that it refracts them. You are looking for this idea either of curvature or of focusing the wavefronts. Now part B, explain how the lens produces this effect. So what we're saying here is, why is it that these wavefronts on passing through that lens are actually curved? All right, why is the curvature of them changed? And the reason for that is in the shape of our lens. Okay, think about simple refraction. When light meets a surface or a different optically dense material, its speed will change. All right. Now, if that light hits a surface and all of the light hits the surface at the same time, then all of the wavefront will be slowed down by the same amount, and therefore no bending or no curving would occur. The reality is, because our lens is curved and because it is thin at the top and it is much, much thicker in the middle, the amount of time that our wave spends passing through that lens and travelling at a slower speed is different at the top to the bottom. So ultimately, the wavefronts that are travelling through the middle of the lens, they are being slowed down for quite a long time, and as a result, the curvature added there is much less than the curvature that is added at the top, where we have got this thinner part of the lens where they are slowed for a much, much shorter period of time. So the key thing here is along the lines of this idea that there is a difference in thickness of the lens at the edges. So by the edges, I mean the top and the bottom. And what that means is that the waves would then be slowed, okay, for different amounts of time. And in that happening, what you find is that the amount of curvature added is different for the 2 different parts of the lens. Another way of saying that is you can link that to refraction. So for the same 2 marks, you could say that it refracts more at the edges because the edges are more angled, and that would equally get you the 2 marks. Okay, so another one looking at pixels and resolution of images, this time in the context of the Atlantis and the Endeavour. So first up, state and explain how many bits per pixel are needed for 128 alternative levels. So basically that question is saying how many and how did you get to that answer. All right, so we know that we've got each pixel coded with 128 levels. So we are saying how many bits allows you to have 128 alternatives. So to find that, we say, well, okay, log to the base 2 of 128 gives us our total number of bits. And when we do that, we get a value of 7. So the bits per pixel will be 7. Next, we're asked to find the amount of information in the image, or rather show that it's less than 1 megabyte. Okay, so to work out the total amount of information in an image, we need to know the total number of pixels in the image, and we need to know the total number of bits that each pixel is represented with. So let's start by working out the total number of pixels in the image. So we've got 700 multiplied by 520, which gives us a total of 364,000 pixels in the whole image. Okay, and we know from our previous question that these particular images are made using 7 bits per pixel. So if we multiply that by the 7 bits per pixel, then that will tell us the total number of bits in our image, which comes out at 254,800 bits in total. And if we then convert that to bytes, we divide that by 8, and we end up with 0.319 times 10 to the 6 bytes. And as we can see quite clearly, 0.3 times 10 to the 6 bytes is less than 1 megabyte. So now we're being asked to work out the ratio, the distance from the camera to the Endeavour divided by the distance from the camera to Atlantis. All right. Now the thing to bear in mind here is this is another one involving measurements from the actual image. So what you're having to do here is say, well, okay, let's look at the differences in the height of the Endeavour compared to the Atlantis. Okay, because what we know from this is that the further away an object is, the smaller it's going to appear. And therefore, actually, we know that the image height is inversely proportional to the object distance. Okay, so inversely proportional to the object distance. So what we do here is we measure the heights of the Endeavour compared to the Atlantis in the image. So again, yours will vary because it depends what size and image you are going from. But mine came out at 0.5 centimeters for Endeavour, and for Atlantis it came out at 1.8. Okay, so in order to therefore calculate the distance from the camera to Endeavour divided by the distance from the camera to Atlantis, what we have to do is we have to take the height of Atlantis and divide it by the height of Endeavour. So when we do that, we take my 1.8 and divide it by 0.5, and that gives an answer of 3.6. So from my measurements, the value for the ratio is 3.6. I think if you're taking this from an A4 document, it comes out at something like 3.7. But as always, as long as you have shown clearly your methodology, you will be absolutely fine and you will get full credit. Now we've got some information about the resolution at the position of Atlantis, and we're now being asked to work out the real length of Atlantis. So again, we are going back to this idea of taking measurements from our image. So what we need to do is we need to say, okay, how many pixels tall is Atlantis? All right, so you take a measurement from your image to work out the proportion of that vertical image, rather the vertical proportion of the image taken up by Atlantis. So when that happens, and again your values might be slightly different, I found Atlantis to be 1.8 centimeters. I found the height of the image to be 6.6. So that gives us the proportion of the image taken up by Atlantis. The total height is 520 pixels, and therefore when you work this out, this will give you the height in pixels of Atlantis. So I ended up with 141 pixels tall. Okay, anything between 138 and 153 here is absolutely fine. So we're saying that Atlantis is 141 pixels tall, and we know that the resolution is 0.24 meters per pixel. So in order to find the length of Atlantis, then what we do is we take our 141 pixels and we multiply it by our 0.24 meters per pixel, and that gives us a length of 34 meters in my case. Again, anything between 33 and 37, as long as you have got a clear method, that is absolutely fine. And the last part then, we're looking at the resolution of the image at the position of endeavour. Okay, so what we can do here is say, well, all right, since we know the ratio, the distance to endeavour divided by the distance to Atlantis, actually, therefore, the that ratio is also going to be equal to the ratio for the resolutions. And therefore, the simplest way to do this is to say, well, okay, therefore, the resolution that we have for Atlantis multiplied by our ratio will give us a value of 0.864 meters per pixel. Okay, and anything between 0.7 and 1.1 would be acceptable there. Nice straightforward lens calculation here. So now being asked to work out magnification, which of course is V over U, and we can see that from our diagram we know that V, distance between lens and image, is 1 centimeter. So if we put that into meters, we've got 0.01, and our value for U is 10 meters. So when we work that out, our magnification comes out at 0.001. Then we need to work out the power of the lens needed to get this magnification. So in this instance, we use our lens equation. Okay, so 1 over V is 1 over U plus 1 over F. We are after power, which is 1 over F. So if we rearrange that, we have 1 over V minus 1 over U. Okay, which in this case, our value for V, as we said, was 0.01 minus our 1 over U. But remembering, of course, that U is negative. And when we work that out, we end up with a power of 100 diopters. Okay, another one looking at distances from resolution and pixel values. A couple of methods you could have used to find this one. I'll go through sort of 3 of them, really. So first off, what you've got is you've got the vertical and horizontal values of pixels. The first way you could approach this is you could approach it from a sort of Pythagoras approach. So you could say, well, okay, if there are 4,096 pixels horizontally and there are 3,072 vertically, what does that make the pixel count across that hypotenuse? And if you do that, you come up with about 5117. So here's method 1. So if you know that to be the case, what you then do is, once again, you are looking at measuring distances. So you measure the length of the arrow that you've got here as a proportion of the length of the whole image from this bottom left corner to the top right. Okay, so when I did that, that was 2.7 centimeters out of 12. Okay, and then I multiply that by the total number of pixels across that hypotenuse, which gives me a total value for the number of pixels for that arrow of 1151. Okay, been told that the resolution is 30 light years per pixels, so 1151 pixels at 30 light years each gives a value of 34539. Okay, or very roughly 34500 light years. Okay, now a bit of leeway here. Your value for pixels can be anything between sort of 1,000 and 1,200. All right, and ultimately then you can get anything between sort of 30 and 36. 1,000 for your value of light years, but that's just one approach to do this. What you could also do is you could use an approximation using just the vertical or just the horizontal. So using the same method, you could measure the length of the arrow and then figure it out as a proportion of the vertical or the horizontal. Okay, so I'm just going to change colour for just a moment. If you do that, then if you took the length of the arrow and you divided it by the height of the image, then that is very roughly a third, and therefore when you work that out, that comes out at approximately 1,000 pixels. Now I am being very, very rough here, but hopefully you can look at your own working, and as long as you've done working, you'll be able to follow it. So there is one option, that you simply say, well, okay, the arrow as a proportion of the vertical height is about a third, giving me about 1,000 pixels, multiplied by 30, there's your answer. Equally, you could use the same argument, but you could do that horizontally. So you could say actually the arrow divided by the width of the image, and that's approximately equal to a quarter, which again, when you look at the width of the image in pixels, is approximately 1,000 pixels. Okay, so there's a few ways you could approach this, but your number of pixels should be 1100 plus or minus 100 pixels. Okay, and then your actual final answer should be 33 plus or minus 3, okay, times 10 to the 3 light years. Okay, more about digital image storing. So you're asked here for the number of alternative intensities for each each subpixel. So each subpixel is coded by a 12-bit number. So to work out the number of intensities or the number of alternatives, we simply do 2 to the power of 12, and that gives us 4,096 intensities or alternatives. Next up, show that one image is about 75 megabits of information. Okay, so once again, we start by saying what are the total number of pixels in our image. So that will be 1920 multiplied by 1080. So that gives us our total number of pixels in the image, which is 2073600 pixels. We know that actually there are 12 bits for every pixel. Okay, so we then multiply that by 12, but we know that that's for each subchannel and that there are actually 3 subchannels, so we multiply that by 3, and when we do that, we end up with a value of 74649600, which is very roughly 74 megabits. Now this last part, question 3, I do need to confess this is actually no longer on the specification, so if you didn't have a clue what you were doing, you can be forgiven. I'll go through it anyway, just in case you managed to have a crack at it or took a stab in the dark. Bandwidth required. Now the key thing here is bandwidth is effectively, it's measured in hertz, but actually bandwidth is the same as saying the number of bits per second. Okay, so the number of bits per second that are actually being transferred. Now what we've got here is we've worked out the total number of bits for a single image, okay, and this screen is showing 120 images per second. So we've got 120 images each with a total number of bits of, if I use my full answer from previously, okay. And when we work that out, you come up with a staggeringly large number, 895795200, which is very approximately 9 gigahertz. But as I say, oversight there, that is actually no longer on the specification bandwidth, so please don't worry too much. Then we're asked to explain the difference between unpolarized and polarized light. Okay, now this is a 3 marks worth, and actually you could do this using diagrams as long as they are drawn in a certain way, but you do need to make reference to the fact that light is actually a transverse wave. Okay, so the first thing to get you a mark here is this recognition that light is a transverse wave, because remember, you cannot polarize longitudinal waves. So light's a transverse wave, or you can explain what the difference is between transverse and longitudinal. So this idea that the oscillations in a transverse wave are perpendicular okay, to the direction in which the wave travels. All right, so there is your first mark. You do need to actually state the feature, the nature of a transverse wave, okay? Then you talk about the fact that unpolarized light, well, with unpolarized light, we've mentioned these oscillations. The key thing here is that the oscillations can take place in all possible planes or all possible directions, really. Okay, so there is your explanation for what unpolarized light is. You could draw it. If you drew it, you'd be required to have arrows on either end, just to signify the fact that the oscillations were moving backwards and forwards. But either of those approaches is fine. So for 1 mark, there is an explanation of unpolarized light. And then your third mark comes from polarized light, whereas with polarized light, what we've got here is we've only got one direction of oscillation. Okay, so whereas with unpolarized light, we've got many possibles, any in fact, we've actually only got one direction of oscillation with polarized light. Okay, this one a little bit waffly, so I wouldn't worry too much about it because the nature of it is such that it's not likely to reappear, but nonetheless we will have a look at some of the marking points. Suggest and explain how the glasses alternately block the light to the left and the right eye. So what you've got is you've got one fixed plane, fixed filter, and one liquid crystal. So the key thing here is that these filters are both going to transmit light polarized in the right plane. Okay, so both of these filters are going to transmit light polarized in the right plane, because that's what they do. Now the thing here is that in order to block out, in order for one eye to be blocked out whilst the other one is able to view, then what we're saying here is effectively the fixed filter, for example, okay, is going to need to be at 90 degrees to the liquid crystal filter. Okay, so fixed filter needs to be at 90 degrees to the liquid crystal to block the light out. And then the last point comes from this acknowledgement that the switching occurs because of this PD. So it says this material acts as a polarizing filter when a voltage is applied across it. Okay, so in order to get the differences between them, you've got the liquid crystal filter is switched on by the voltage. Okay, so that liquid crystal is switched on by the voltage, or you could say that the voltage is switched from one eye or lens to the other alternately. Okay, or you could say that actually the there is a signal from the TV which will trigger the glasses switching. Okay, so a little bit tricky that one, but don't worry too much about it. Okay, looking now again at a lens diagram, slightly different emphasis this time. State how the diagram shows the object is very distant from the lens. Remember, the further the light has travelled, the less the curvature it will have. Okay, so the key thing here is that actually as these wavefronts arrive at the lens, these wavefronts are flat. Okay, so any words to that effect? Anything to signify the fact that these wavefronts are flat. It's not sufficient to say they're parallel, all right, but it is okay to say that they are flat. And then add 3 more wavefronts to the diagram between the lens and F. There's always 2 things you have to get right with these sorts of ones when they are 2 marks. The first of which is they must be converging. Okay, so you've got to have this idea that that lens has added curvature and therefore they are converging onto the focal point. All right, and the second thing you have to get right is you have to acknowledge that there is no change in wavelength, and you do need to do this carefully. Okay, so what you have to do is very roughly look at the value for the wavelength in the light wavefronts before they hit the lens, and then you have to match that. Okay, and it's worth doing that properly with a ruler, okay, because that is one where you really will have a mark taken off you if it is not clear that your wavelength has stayed the same. Nice simple wave calculations now. So frequency we're being asked to find here, which if you recall is wave speed divided by wavelength. So the speed of our ultrasound is 1500 and the wavelength is 3 times 10 to the minus 4, giving us a frequency of 5 times 10 to the 6 hertz. Then we're being asked to look at the number of oscillations in a pulse. All right, so number of oscillations is an oscillation is one complete wave. All right, so there's a couple of ways you could do this. You could say, well, all right then, in order to do that, we know that the relationship between time period and frequency is that time period is 1 over f. Now the time period is the time for one complete wave. All right, and therefore we haven't got a complete wave necessarily, but what we have got is we've got the time of the pulse. So we could do 0.8 times 10 to the minus 6, because that's our 0.8 microseconds, and we could multiply that by the frequency of our wave, and that would tell us the number of oscillations that we've got, which comes out at 4. The alternative way you could do this is you could say, well, actually we know the speed and we know how long the pulse duration is. Okay, so you could say, well, all right, it's 15,000 meters per second, and the time that lasts for is 0.8 times 10 to the minus 6. So what you've done here is a speed multiplied by time. Speed multiplied by time gives us a distance or a length. Okay, that would tell you the total length of wave in that time. And we know that the individual wavelength is 3 times 10 to the minus 4. So if we then divide that by our 3 times 10 to the minus 4, that would also give us a value for 4. Again, another lovely straightforward one, calculating the power of the lens in diopters. So remembering that power is 1 over focal length, so 1 over 0.2 meters gives us a value of 5 diopters. Now we're looking for the curvature leaving the lens. Okay, so in this instance we are looking for 1 over v. All right, remember 1 over v is 1 over u plus 1 over f. 1 over u is also the curvature of the light arriving at the lens, which we've been told is minus 0.4. So our value for 1 over u is minus 0.4 plus our 1 over f, which we just calculated, which was 5d, and therefore our value for 1 over v, which is the curvature leaving the lens, is 4.6. So 4.6 diopters. Quick little image processing question here. Okay, so you're being asked to calculate the new pixel value, having been told how the pixel has been manipulated. So hopefully that's fairly straightforward. You simply take your 80, you subtract the 80 and you times it by 2.1, giving you a value of 0. You then repeat that for the value of 200. So 200 minus 80 multiplied by 2.1 gives you a value of 252. So 1 mark for each of those. Describe how this image processing has improved the image. The key thing here is that you have improved the contrast. Okay, so the differences between the lights and the darks have got better. Okay, so you've improved the contrast or you've improved the range of the grayscale. Either of those is absolutely fine. Okay, or words to that effect. It is not sufficient to say that it is brighter, okay, because actually it isn't, and it's not sufficient to say that it is clearer, because it isn't. All right, remember, brightness is about increasing all the pixel values. What this process has done is it's stretched those values over a larger range, and therefore it has improved the contrast. Okay, curvature of waves arriving again. So curvature of waves arriving is 1 over u, and we know that u in this case is 1.25 meters, or strictly speaking it's minus 1.25, and therefore the curvature here comes out at minus 0.8 diopters. Now we're being asked to work out the power of the lens needed for someone who needs lenses to read a book at a distance of 0.25. So what we have to do is work out our new value for the curvature arriving at their eye when they are looking at that book at 0.25. So there's our first step, to work out the new value of that light, and when we do that we end up with a value of minus 4 diopters. So that gives us the curvature of the light arriving at the person's eyes when they are looking at something 0.25 meters away. versus our previous question, which was minus 0.8, which was the curvature when they were looking at 1.25. So what we're now saying is actually the power of the lens required for this is the difference between those two. So our minus 4, which is at 0.25, plus that lens should give us our minus 0.8. And when we work that out, we end up with a value of plus 3. Okay, so another one looking at images with numbers of levels of intensities and bits and working out the amount of information in an image. Apologies, it was absolutely impossible to track down the original image. So what I did was I removed the part of the question that I thought needed the image, although actually on looking at it again, I realised that part 2 would have been very difficult without the actual image, but not to worry. So what I'll do is I'll tell you the piece of information that you're missing that would have allowed you to do part 2, and that is that this image is 500 by 300 pixels. Okay, that would help you with part 2, but we'll come on to that later. So it's got 16 alternative intensity levels. Show that 4 bits are needed for 16 levels. So what we're saying is how many bits give us, so log to the base 2, how many give us 16, and the answer there is 4. So part 2, as I say, very tricky to do if you don't know that the image is 500 by 300 pixels, but we'll go through it anyway. So if you want to know the maximum number of bytes to store that particular image, well, firstly, we need to know the maximum number of pixels in the image. So it's 500 multiplied by 300, which gives us a total of 150,000 pixels in the image. And as we can see from the previous question, 4 bits in the image, which means that each pixel has a 4-bit code. So therefore, we need 4 bits for every single pixel. So the total number of bits that we've got is 600,000. Okay, but we're being asked to look at bytes, so we then divide that by 8, and that gives us a value of 75,000 bytes, or 75 kilobytes. And then part 3, again, with having not been able to do part 2, it is highly likely that you wouldn't have been able to do part 3. So by all means, pause here and give it a quick go. What you've got here is you've also got the shortest movie in history, because it's 90 seconds apparently at a rate of 5 images per second. But we know that each image is 75,000 bytes, okay? And we know that we've got 5 images a second. So for one image at 75,000 bytes, 5 images a second gives us the total information per second. And the movie was allegedly 90 seconds long, which gives us 33750000, or 34 megabytes. And then last one here, nice short one to finish up. Complete figure 7.2 to show the wavefronts to the right with a lower refractive index. Now, refractive index is a measure of how much the light is slowed down by a lens. So a high refractive index means that it is going to refract the light a lot or add a lot of curvature, and a low refractive index, it would add less curvature or refract it less. So in this instance, we've got a lower refractive index. So the two things to watch out for here is your first thing is your focal point should be further away. So your focal point can be anywhere as long as it is clearly further than the one in 7.1. And then the second marking point here is, as previously, you add these wavefronts, but the wavelength should be maintained. Okay, so as best you can, you measure as closely as you can what that wavelength is, and you keep that exactly the same because, of course, the wavelength doesn't change. State with a reason whether the power of this lens is larger, smaller, or the same as that of the original lens. A couple of arguments you could put forward here. The bottom line is it is actually smaller. Okay, the first argument you could give, well, you could give the fact that power is 1 over the focal length. And in this case, focal length has increased. So there is one argument for it. You could say that it is smaller because actually the light isn't refracted as much. Okay, that would be fine. Not refracted as much, that's maths, all right? And then another way of looking at it is this idea, again, as we like to keep going back to, is that it adds less curvature, okay? So any of those would get you that last mark.